Okay, moving on to the temperature rise method. I think I picked that first because it tends to be the most popular in the educational setting. You basically rewrite the sensible heat equation to get CFM. And as everyone knows who's in education, watch your units of measurement. You know, it's going to be, the airflow is going to be in CFM. It's got to be BTUs per hour output. And the delta T's got to be in degrees Fahrenheit. If you don't get those correct, all bets are off. So you need to know two things, the BTU output and the change in temperature. One thing you got to be aware of, that 1.08 is a simplified equation. It's got baked into it the density of the air. So if the air density is different than standard air conditions, that 1.08 factor is no longer true. It can vary 1.05, 1.07, 1.09, depends upon the air density. And again, density is affected by temperature, humidity. Oh, those are the things we're trying to change in the system. So, you know, you might be chasing your tail. The good thing, though, is with online calculators, you can actually do these kind of calculations and put in the local humidity, the local air temperature. If it's important to you to get a more precise reading, you can pull these values together. There's apps that do it. CamelSoft is one that makes some. There's also a website called Residential Energy Dynamics. They're also called residentialenergydynamics.com. It's got an online calculator, free. You can enter in your zip code, and it puts in your local weather data. There's a lot of calculations that are done for residential energy management, airflow, et cetera, in that online program. So there's resources available, so you're not just stuck with that. You can use this kind of temperature rise method if you have a source of heat, of course, because you're measuring temperature rise. You're backing it out of the sensible heat equation. But you may have variations in fuel and even the motor heat of the distribution air fan. If you don't account for that, that's going to be some extra heat that wasn't coming from the fuel that you won't have accounted for in your BTUs output, which is going to throw off your reading. So again, just be aware of what you're building your information on. You also have to let the appliance rise to steady state efficiency, which in electric isn't a long time, but with other fossil fuel appliances may take a while for the heat exchangers to heat up. In order to get the BTU output, you need to know the BTU input, and for a fossil fuel system, is it okay to use that sticker? Not better, it's not okay to use that sticker. You can't use the AFUE, you just can't use it. That's the government standard test so you can compare different types of heating appliances. It is not the combustion efficiency number. The combustion efficiency number is going to be a real-time number from the steady state efficiency that you get out of the system. So like you said, you have to use a combustion analyzer to get it for fossil fuel. The other thing I sort of glossed over is variations in fuel. Just tell a quick story. I was up at the labs in Cleveland, used to be the American Gas Association labs. They have what's called a WOBE calorimeter, which is about the size of the corner of this room here, which allows them to develop the heating content in the gas that's coming in, because they're doing certification testing and they need to know, their engineers need to know what the fuel content was, the energy content of the gas, and they pull it off the main line of whatever the utility is up there. And I asked if I could take a look at the strip chart recorder that's sitting there stacked in the hallway, and I pulled out a few sheets, and there was a variation over a couple hours period of time of around 200. So it can be pretty significant, the variation, and they're just using the gas that everybody else uses. They aren't using tank gas. To get the BTUs output, you need the BTUs input times the steady state efficiency, which comes from a combustion analysis. Or if you're doing electric, you can just convert the kilowatts to BTUs per hour. So that's a lot simpler. But you have to measure the temperature rise of the air. That's the important thing. So the placement, as this gentleman mentioned, out of line of sight of the heat exchanger. Otherwise, you're going to get a radiant effect from the heat exchanger, which will warm the surface of the thermocouple or whatever temperature device you're using and affect that reading. You want to know just the temperature of the air. And if your air isn't all traveling across where you're measuring, and it's bypassing from some other device, that, like a humidifier that may be in the system, you're not going to get, or ventilation, you're not going to get a good reading from that. Again, so it's things you got to watch out for. So this simple air temperature probe that might be, $100 or so to make a measurement. If you don't follow a process, you're going to get a sort of a squishy, fuzzy number. Okay, be aware of that. That's what I'm saying. I'm going to pass around a thermal anemometer, which is one of those radio sensors that hooks to an app. And again, with those, you can get some improvements in the measurement because they're rolled in, they're baked into the app. But take a look at that as I pass that around. I'll show you an illustration. Was there another question? Okay. It works based on wind chill again of a heated bead. It's proportional to the air velocity. That is one of the devices I'm sending around. That's the tip of a standard pen. That little tunnel in there with the little dot, it's about the size of a period and maybe like 14-point font. That little tiny dot is where actually what's the device measuring the airflow. And as you look at them coming around, the other one has a different configuration, but the same basic science going on. This only knows about the airflow where that little tunnel is, okay? That's why you have to do a traverse and move it around. It doesn't know what's happening a ½ inch away. And if things aren't stable and uniform, that's going to be meaningless. If you have a variation in your airflow, you need to account for it. That's why you need to do traverses with these devices. There's also a thermistor built into these, which provide temperature compensation. So that factor we talked about, that huge factor of air density, a lot of these devices take care of it themselves, okay? So it's something to look into when you buy a device, but I would say almost all thermal anemometers now give you the air temperature as well as do the thermal compensation. So they take care of that correction factor that's affected by the air density, because more dense air takes away more heat as it's flowing over this little bead on the device. It's got a pretty broad range, and this is where the 2018 edition is going to be a little bit better, because I'm going to use some documentation from the ASHRAE 111 standard, which talks about ranges and recommended applications, and dig into that further. They're pretty easy to use, but you have to also be subject to contamination because it uses the wind chill effect or the cooling. If that gets coated by any oils or dusts or anything like that, then it's going to become an insulation to it, and it's not going to work the way it did in the factory. The other factor with these, and I think it's on that 405i that I'm passing around from Testo, the little orange handle. Look at the tip of that as it comes around. It's got an arrow engraved in it, molded into the tip of that. That's the direction it was calibrated in. That's the direction you should use it in. So look for these kind of hints and features in the products that tell you how to use them in a more refined or better manner to get more out of them. You need to find out from the manufacturer what you can clean it with. So I'm not sure on that one. There's subject contamination we mentioned, and there's a small intercept area. So it only knows about what's happening in that little tiny area where the sensor's located. It doesn't know about anything else. So you have to move it around to give it an idea of the total bulk airflow. And I say in-duct measurements are the prime application for it, unless you're just looking to see if flow is present for leakage. You can use it, it supplies and returns, but it requires an awful lot of care and measurement. So generally, I don't recommend it. I may change my opinion on that. The Pitot Tube, which got passed around, you familiar with that? Most people are familiar with the Pitot Tube? Okay, so it's a tube in a tube, measures the total pressure coming into the tip of the probe and the static pressure from the external ports. There's an equation which takes you from the total and the static, which you connect to your manometer. The difference between those two is the velocity pressure. The velocity pressure, when you take it through an equation, it's a fluid dynamic equation. The square root of the velocity pressure times 4004.4, 4005 will give you the velocity, the speed of the air in feet per minute. However, that 4005 has baked into it, guess what? Density, okay? So a lot of the meters have built into them correction factors. You can give it the humidity, the temperature of the air, even the barometric pressure, and some of them do it automatically, that built into it, that'll correct that, and they'll use a custom equation for the conditions that you have at the time you're making the measurement. Again, so that's why these things cost different amounts, because they give better and improved performance. And it's not just because somebody wants to charge more, they actually do give better performance, and if you need that performance. So density impacts a pitot tube. The lower velocity limits, be aware of this. You want to use a manometer that has finer resolution when you're at lower velocity levels. If you pick the wrong manometer, you're going to get a bad reading. It's going to be inconsistent. And it's got a smaller intercept area, just like the thermal, the hot wire. Small intercept area, so it's got to be traversed or moved around to get an idea of the average flow field that's moving through the duct. So doing a traverse, getting to that, there's two types, and the way I explain it is the timed average, and I call it like painting with a roller. Okay, so you want to be smooth and steady to apply a good layer of paint, and you want to cover every surface that you're measuring across when you're doing the traverse, either a supply, or return, or inside the duct. You want to try to get as much of that paint on there as evenly as possible. So if you do 2 rolls on the top run, the top traverse, that's not a good measurement. You'd have to do, if you did 2 of them, you'd have to do it evenly, whatever you're doing. You would also want to use the same speed. If you run a roller too fast, you get splotches or gaps in the measurement. If you run it too slow, you'll get a higher density or thickness there, so you're biasing the measurement. So again, think of roller painting. You want to do a nice, even, smooth job to do that. Point averages is like paintball. You want to get the area covered the best you can by taking point measurements, and you don't want to hit one area twice, but you're going to be trying to hit it with paintball an even amount of times to get an idea of what the airflow field looks like when you're taking an average. Timed averages, getting into a little bit more detail there. They can be a little bit faster, but it depends on your consistency. Again, if you're a good roller painter and being able to do that consistently, and also acknowledging the hot wire and the pitot respond really quick, and the rotating vane, the mini vane, which we passed around, you got to watch the display on that and see how it varies as you're moving it across the flow field. So be aware of your measuring technique. It makes a difference. Point average is considered more conventional. You'll find it in the testing, adjusting balances, the NEB world, the AABC, the TAB, TABB. But you do need to determine your target points, where you're going to take them. And there are some industry standards there. We actually took the log-Chebyshev method and put it into, it's usually put in as a percentage of the dimension of the duct, which is hard to use in the field because now you got to pull out a calculator and make sure you do it correctly every time. So we went ahead and put on our website in our resource area a rectangular traverse with different types of rectangular ducts, and we actually put it together with inches as well as millimeters. And we did the millimeters because we saw that it's easier to find a millimeter than it is to find a fraction of an inch on a chart. So if you want, if speed and precision, so we have a magnetic millimeter rule that you can use to slap to a ductwork, mark it with your Sharpie, and move pretty quickly in making those measurements when you put the holes in the ductwork to take the measurement. You want to hit those target points pretty well, so you need to know where they are. And you can do a traverse with the mini vane, the hot wire, and the pitot, or I shouldn't say you could do it, you need to do it with those. Just some people are acceptable with putting the probe in the center of the duct, oriented for maximum velocity, multiplying by 0.9 and saying that's what it is, because most ducts behave the same way. That's acceptable, but know what you're getting. Maybe in an instructional mode, you want to go ahead and take that time to take the traverse, compare it to the 0.5 or 0.9, and now you got a teaching moment there to talk about flow fields, crank the blower speed up, and see what that does. If you get more static friction at the wall, your number goes off of 0.9. So work with this as an educational teaching moment. The true flow plate, which we mentioned at the very beginning, is a bulk measurement. It's actually a device that slips in the filter slot. Has anyone here seen a true flow plate? Okay. They run about $800. You get 2 of them for the different typical residential filter return slots. They've got an array of Pitot tubes in there. It's got a plexiglass plate with holes that allow it to get the total pressure. And then on the back, the shielded area gets the static pressure. So you hook it up and it's all calibrated in the meter. Those 2 meters we passed around actually have calibration profiles for this true flow plate. The thing about it is it's a bulk measurement, so you connect it correctly, connect it to a correct manometer, and you have the CFM reading. So in a lot of energy programs, things like Cool Smart, Cool Saver, you might have heard of these before, they're using these because they can deploy with contractors and not have to worry that everybody's doing a traverse the same way. So these give you quick snapshot measurements.
What are those sizes?
I believe one dimension is 14 and one is 20. No, that's the Energy Conservatory. Yeah, they're the only ones that make this. That actually was a government developed and patented, and they licensed the patent to make it. The 2, Trutech and the Energy Conservatory, their manometers have baked into them the equations, so you can hook it up and get the reading directly out of it. You get the numbers straight out of it. So they're pretty fast to set up. They're adjustable. They have little flap panels you can put on them to accommodate, and they wedge in there and they fill the filter slot or the central return. It's very close to the running conditions because in order to use these, you first take a static pressure measurement. As a system, as you walk up to, you take a static pressure measurement. So you account for what's happening with the filter and the whole static pressure of the system. You remove the filter, put this in, enter into the device your static pressure, and it uses a curve inside to curve fit it and correct it to give you that CFM number. So there's an intermediate step. You have to take an extra measurement of the static pressure of the system. And you need a specific digital manometer, otherwise you'll be doing a sheet of calculations on it. So this is for system airflow or central returns. And I have heard people remark that this doesn't have a huge system effect. If you had 2 central returns, you can wedge it in, take one reading, go take another reading, add the 2 together. That's your total return airflow. There's no duct leakage. That's probably your system airflow. Okay, I say probably. So with the manometer, it's 2,000, by itself 800. The manometers run anywhere from 1,000 to 1,400 for those specialized manometers. Static pressure tips. I passed around a couple static pressure tips. Those are the ones with the blue and the red flanges on them with the magnet. So they look like a pitot tube or a mini pitot tube, but they're not. They're actually blocked off at the tip. That's where it varies or is different from a pitot tube. And it's measuring the static or the balloon pressure inside the ductwork. By itself, it's not it's a measurement of pressure only, a static pressure tip. We'll talk about how you apply that to get airflow in a moment. So they're pretty easy to use, pretty cost effective. I think we sell them for like $14 each, around that or so. You do need a manometer to get the reading out of them, but they don't directly equate to airflow. You need to know another step in between that airflow chart, and we'll go through one of those, an example in a moment. So this total external static pressure, the manufacturer actually profiles the heat exchanger or the evaporator coil. They'll actually use another device to measure the CFM, probably like a lab grade device, and they're going to run it up through all kinds of speeds that their equipment normally runs through, and then measure that pressure drop with a precision manometer and develop a table of values that you can then take in the field and use. Just to kind of orient you to this, this is a range of a fraction of an inch of water column. So you can use a slack tube manometer, you can use an incline manometer, you can use digital manometers, you know, the things that are in like the $100 range to $150 range. However, ECM motors make everything different, and we'll explain why that is impacted in a moment. So this would be an illustration of applying that static pressure tip with the manometer to a situation where you have an AC coil or a heat exchanger, but you need that table of pressure profiles in order to get the airflow from it. And there's no generic table. You might see similarities between types of equipment, but I'll show you two stark examples where you can't really compare. The results depend on the manufacturer's table. Again, so it's specific to the equipment and the configuration, and then the known resistance that you're going to pick up from the static pressure drop can change, and we'll talk about that specifically and give you an example. You want to be careful about where you place it. You don't want to drill into coils or wires. And the cost actually is a little bit lower than that when you consider this smartphone manometer I passed around. Your costs are starting to drop with doing this, but again, it's the kind of thing that involves some interaction and some knowledge of the user to get a good measurement from it. So this is a typical airflow pressure drop chart that you would see in the manufacturer's literature for a residential system. Interesting thing here, that says wet cooling coil. So that's the way they tested it in the lab to get these numbers. That's the way they intend you to test it in the field to get the same kind of numbers, same kind of performance. But how wet is wet? And what happens if you don't have enough humidity to cause it to be wet? Just be aware, you're going to be off in your number, okay? How far off? Somebody's probably going to ask that. I can't tell you because it's going to vary.
Do you have a number in your head?
Nope. I have no numbers in my head at all.
I've typically done that back and forth on drying wet coils, and I've seen about a 10%.
10%, okay, very good. That's the first time I heard someone speak up with that. So, these are also coil-only airflow ratings, so don't take the measurement over the heat exchanger too, because that's not where they did it in the lab. You got to replicate the lab test in the field with some simple instruments. Try to replicate as best you can to get some good numbers from this. The charts also are all different the way they're laid out, so you have to spend a couple of minutes just understanding. This one has inches of water column and CFM. The CFM is in the top row, the inches of water column is in the chart here, and then the metric equivalents are down below. You also have to match it up to the coil in this case, because it's a coil-only rating. You'd have to make sure you're using that coil. So say if you're using that coil, now all you have to do is look at that line and get a ruler out. This will make it a little bit simpler to do that. That'd be a good exercise again for students to do that. Show them how to read these kind of charts, show them a couple different charts so that they're familiar with it. Say you get a reading from your digital manometer or your slack tube or your incline of 0.14 inches or thereabouts. You can say it's about 1100 CFM. Now notice here that it's a difference of 0.02 inches of water column is 1200 and 0.03 difference is 1000. So it's a plus or minus 10% for just the resolution of the manometer usually. They're usually not better than a couple of hundredths of an inch of water column. So again, if you're looking to compare this with something else, the higher quality tools you use, the better information you're going to get from it.